So my name is Rotem, and I'm here to tell you about joint work with Renato Renner and Thomas Vidic. The title is Simple and Tight Device-Independent Security Proofs. I will start with... Use this one. Okay. It's not for short people, this one. So, okay. So like this, it's fine? Better? Okay. Perfect. So I will start with a very brief introduction to device independence, since Roger already covered the important stuff in a tutorial this morning. And then I will explain what is the main difficulty when proving security of actual device-independent cryptographic protocols and show you how our results solve this difficulty. I will say a few words about the proof technique and finish with the outlook. Okay, so let's start with the introduction, the concept of device independence. So the idea is that Alice and Bob share some uncharacterized device. Okay, so this is this box. They don't know what's going on inside, but they can interact with it using some known protocol, for example, device-independent QKD protocol. Okay, so they interact with this device, and then in the end, they can choose either to abort or they accomplish a certain task. Okay, for example, perhaps they output a good key. Okay, and the reason that it is possible to achieve cryptographic tasks using some interaction with uncharacterized device is, as Roger explained, due to the existence of Bell inequalities and non-locality. Okay, so I will use the terms Bell inequality and also Bell game or just a game. So let me explain it briefly. So here we have Alice and Bob's device. It's a two-component device. And inside there is some bipartite quantum state. We don't know what it is. Okay, this is this row here. And as in all scenarios when dealing with Bell inequalities, during the time of the interaction, the time of the game, these two components are not allowed to communicate. Okay, so this is this wall that Roger had. Okay, now the game starts, the interaction starts. So Alice and Bob use their inputs, X and Y in this talk, to interact with their components, and they get the outputs A and B. And then the game is defined via a winning condition. Okay, this is a function here, W, of the values of A, B, X, and Y, a function to 0 and 1, stating whether they lose or win the game. Okay, so this defines a specific game. Once we have a game and we have a specific device, we can talk about the winning probability of the device in the game. Okay, so this I denote by omega. This is just a number between 0 and 1. Now we can write a Bell inequality. So Bell inequality basically says that for any classical device with a winning probability omega c, so this just denotes winning probability of a classical device, the winning probability is always upper bounded by a certain value I. Okay, so no classical device can do better in the game than this I. A quantum advantage or a violation of the Bell inequality is the existence of a quantum device, so some quantum state and measurements, such that the winning probability of the quantum device is greater than this I. Okay, so there exists a quantum device that can do better than any classical device. Okay, and the important thing, as Roger explained, is that once we have a violation of the Bell inequality or some quantum advantage, then what we learn is that there is some secret randomness or some entropy in the outputs of Alice and Bob with respect to some adversary that holds a purification of Alice and Bob's state row. Okay, and this is the main ingredient and the important thing to actually have device-independent security. Good. So these were the ideas, the important stuff, but still we get into very big difficulties when we really try to prove security of actual protocols. So now I will explain what are the difficulties. So here I denote, again, our device. We have the two components of Alice and Bob, but now I also denote another component for Eve. This is just a purification of Alice and Bob's state, okay? So inside there is some arbitrary tripartite state, any state inside. We don't know what it is. Now, what we just said is that if we know what is the winning probability of this device, then we can somehow certify the amount of entropy that comes out of it. But if we're just given this small device, then Alice and Bob can play the game once. They either win or lose, but from this they cannot conclude anything about the winning probability of the device. Okay, so they don't know what the winning probability of the device is, and therefore they cannot certify any randomness. Okay, now the obvious thing to do is just to consider this option, so the IID case, okay, independent an identical case. So here I just have now many identical copies of the small device, okay, and they're all independent of one another. These are these tensor products here. And now what Alice and Bob can do is they just play the game many times. Each time they play the game with a different device, okay, and exactly in the same way. Now they can collect all the statistics. They can see whether they win or lose in each of the games. And from this, they can now estimate, using standard statistics, what is the winning probability of just one device like this. Now they know the winning probability, so they can also, they also know what is the amount of entropy that can be extracted from this one device. And since everything is identical here in the devices and everything is independent of one another, then we know that the total amount of entropy is roughly the number of rounds, the number of games, or the number of devices, times the entropy in just one device, in just one game. Okay, so this is something which is relatively simple to understand. Okay, so in the sense that in order to understand what is the total amount of entropy, it is sufficient to understand what is the relation between the winning probability and the entropy in just one small device. And apart from this is just standard statistics. Okay? Unfortunately, and especially in the device-independent scenario, this is a rather strong assumption to assume that the device actually looks like this. Okay? If we don't want to assume anything about the structure of the device, then why should it look like this? And in particular, it means that there are no memory effects. So what happens here in the last device is completely independent of what happened before. Okay? So this is, it's a very strong assumption to assume. And for those who are familiar with the Finetti theorems, let me also mention that they're not useful in the device-independent scenario in general. Okay, so the Finetti theorems are usually used in order to say that actually it's enough to prove security in this case, and from this a general security follows, but here this is not the case. So in device-independent security, we don't have such a general technique like the Finetti theorem. Okay. So we have to prove security in the general case, not just in the IID case. So what is the general case? In the general case, we have three big components. Okay, so each big component to each of the parties. And inside there is some arbitrary tripartite quantum state. Inside of Alice's component, we don't know what's going on. Okay, we don't even know if there are subsystems. It can be anything. What we do know is that we can choose a protocol that has a sequential interaction with Alice and Bob's components. Okay, so what do I mean by this? I mean they can play the games sequentially. So they first play the first game, the input x1 and y1. They get the outputs a1, b1, and only then they go to the second game, x2, y2, and get a2, b2, and so on until they get to the last round of the protocol, and then they input x, n, yn, and they get the outputs an, bn. Okay, so this is a sequential interaction with Alice and Bob's component. On Eve's side, we don't know what's going on. Everything can happen. Okay, it's a general quantum adversary. Good. So let me mention a few words about previous works. Okay, so it all started with two famous works by Eckert and Myers and Yao that basically gave the first main ideas. And then in another very important work by Barrett et al., they combined these ideas to what we call today device-independent QKD. They also gave a first proof of concept that it is indeed possible to extract one output bit, one secure bit, basing the security only on Bell inequalities, but for the perfect case when there is no noise at all and everything is perfect. Okay, then several years later, Pironio et al. Considered a stronger case, so it's not just a proof of concept, but really a protocol that can tolerate noise. And extract many output bits, but they considered just the IID and asymptotic case. Okay, so it means now that they have infinitely many copies of these smaller devices that I had in the previous slides. Okay, they're all independent, and there are infinitely many of them, and they're all the same. Okay, and for these, under these assumptions, they achieved the optimal rates and noise tolerance that are possible for the protocol that they considered. Okay, around the same time, there were many other works dealing with similar assumptions, but this one is the most relevant for us now, so I mention only this. And then finally, recently, people managed to prove general security. Okay, so in the case where there are only these big components, not the smaller devices. Okay, so we have the works by Reichardt, Vidic, Miller, and together with their co-authors, they proved the general security. But there was still a gap open, so these works are rather complex, and the rates and the noise tolerance that they achieve are far from these rates that were achieved for the IID and asymptotic case. Okay, so since this gap was left open, it wasn't even clear whether there is a fundamental reason for the gap or whether it's just a technical difficulty and actually general adversaries, quantum adversaries, are just as strong as the IID adversaries and not more. Okay, and this is what we would like to solve now in our work. Okay. So before I start the contribution, let me just mention that we work in the standard setting, okay, in device independence. So Roger mentioned some of the assumptions, and all of the relevant assumptions are listed here, and you can see them later. But this is really the standard setting. And also, as in previous works, we allow for communication between Alice and Bob and between Eve to Alice and Bob between the rounds of the protocol. This is just important for practical reasons, because it means that in an experiment, it's possible to distribute the entanglement on the fly. Okay, so it's not necessary to create large-scale quantum memories. Okay, so this is nice. Okay. So our main contribution is a general framework which consists of a flexible protocol and analysis to prove security of many device-independent protocols. Okay? Basically, the proof technique is a reduction to the IID case, okay, in the sense that in order to get the full security proof, it is really sufficient just to understand the case of one small game, okay, just what happens in one small game, and from this you get the entire security proof. So we get back to a simple structure of security proof, which is nice. Another advantage is that the reduction is virtually lossless in terms of parameters. Okay, so whichever parameters that we can get for the IID and finite statistic case, we can also get more or less for the general quantum adversary. Okay, so we get tight results, for example, key rates and noise trade-offs. Okay. As concrete examples, we apply our framework to device-independent QKD and randomness expansion, both based on the CH/SH Bell inequality, and let me show you some of the results. So here we see the device-independent QKD key rates. So we consider a very basic device-independent QKD protocol with just the honest implementation is just with qubits and some simple noise model. What we see here is the key rate, so the length of the key divided by the number of rounds as a function of the number of rounds. And the different curves are for different quantum bit error rates, so different amount of noise in the channels. And of course, as the number of rounds increases, then we have better key rates. The important thing to see here is that actually the key rates that we get are pretty high, and they are also comparable already to the key rates that are achieved in standard QKD, like BB84. Okay, so although we do things in a device-independent way, we still get key rates which are pretty high. So this is nice. Another nice plot is the following. Here we see now the key rate as a function of the noise, okay, of the quantum bit error rate, and the different curves are now for different number of rounds. This blue curve, we get it for n number of rounds, which is 10 to the 15. Okay, the important thing is that this curve was also achieved in the paper by Pironio et al. For the IID in asymptotic case and was shown to be tight there. Okay, so it means that although we prove security in the general case against general quantum adversary and consider finite statistics, then as the number of rounds increases, we get to these tight key rates. Okay, so it closes the gap that I mentioned before. Okay, few words about the proof technique. So as I said, we consider a very basic and standard device-independent QKD protocol. The first stage is just this sequential interaction with Alice and Bob components, where they just play the game one after another. And then a second stage is one-way classical post-processing, privacy amplification, error correction, all of these kind of things. Okay? What we do in the proof is we use the sequential structure of the protocol that I mentioned in this picture in order to bound the total conditional smooth mean entropy. Okay, so this is this quantity here. The formal definition is not relevant for us now. So A here is all of Alice's output bits, so A1 to AN, and the E is all of Eve quantum side information. Okay, so all of the information of the adversary. Okay, and this should be evaluated for the state in the end of the protocol condition on not aborting the protocol. Okay, we do this, we get a bound on the smooth mean entropy using a new chain rule for entropies, which was developed by Dupuy et al. Recently in a paper called Entropy Accumulation. And using this chain rule, and our protocol analysis, what we get is that the total amount of entropy is roughly the number of rounds in the protocol times the entropy in one game. Okay, so we get back to the simple structure that I mentioned for the IID case, where it's only necessary to understand what's going on in one game. Okay, the relevant one game quantity, so the relevant entropy that should be plugged in this red part here, is just the conditional von Neumann entropy, so it's a standard quantity, and this should be evaluated for all states with a given Bell violation. Okay, so you fix the Bell violation, then you need to evaluate this von Neumann entropy. So for the CHSH, for example, this is AI is just a bit. Okay, so this is a very small quantity. Okay, and it's indeed a standard quantity. So for the CHSH, a tight bound was already proven in the Pironi et al. Paper, so we could just use it to plug it in our framework. Okay. So to finish, let me summarize what we have and what still needs to be done. So we have a general framework to prove security of device-independent protocols. It allows us to get simple and tight security proofs. Okay? As concrete examples, we apply it to device-independent QKD and randomness expansion protocols based on the CHSH Bell inequality, and it can be interesting now to apply the same framework to other protocols and other Bell inequalities. Parameter-wise, we get parameters which are significantly better than what was known before, and they're actually almost feasible with today's technology. So it's a step forward in actually getting to implement these device-independent protocols. And in essence, what follows from our work is that the best adversarial attack is indeed the IID attack. Okay, so a general quantum adversary is in some sense no stronger than just the IID adversary. Okay, so we close this fundamental gap that was still open before. Okay, so what's next? So I showed you that the key rates that we get are optimal, but this is true only with respect to the specific protocol that we consider and that was considered before. Okay, but still, perhaps there are better protocols, device-independent QKD protocols that can be considered. For example, maybe different Bell inequalities, instead of the CHSH, can certify more randomness. Or two-way classical post-processing instead of one-way classical post-processing can help. And once we consider this modification, there is no need to prove security from scratch. Okay, you can still use the same framework that we have, but just with small modifications. Okay, these modifications are relevant not only for a theoretical point of view, but also for the experiment. So with the current protocol, the detection efficiencies that are required in order to get positive key rates while not opening the detection loophole are still relatively high. Okay, so either we push the experiment a little bit farther and we get better detectors, or perhaps these modifications can help us achieve already implementable protocols today. And a final open question, which I find interesting, is the following. Back to the theory side, so I told you that the relevant one-game quantity is the von Neumann entropy, this quantity here, for a specific Bell violation. So my question is whether there is a general technique to get a bound on the von Neumann entropy. For the mean entropy, this is indeed possible using the SDP hierarchies, okay? But for the von Neumann entropy, I don't think there is such a general technique. If there is one, then this can be really useful, because now for any Bell inequality, we can choose the Bell inequality, then plug it in this general technique to get a bound on the von Neumann entropy, and then plug it in our general framework in order to get the full security proof. Okay, so this will simplify a lot of things. And with this, I end. Thank you very much.
Do you have any questions?
Nope.
Arnon?
Thanks for a great talk. It's great to see these results. I was just curious about when you say it's simpler than previous proofs, how you're quantifying that.
So let me get back. So what I meant by simple is that really, first of all, yes, specifically this, that it is sufficient to understand just what happens in one game. Okay, so now if you want, for example, to apply our proof to a different Bell inequality, Okay, the only thing you need to do is you don't need to prove security from scratch. You just need to understand what is the relation for this new Bell inequality between the winning probability or the violation of the Bell inequality and the amount of entropy. This is one thing. Another thing is that the one game quantity that you need to bound is just the von Neumann entropy. Okay, so it's something that I guess everyone in the audience are familiar with. So in this sense, it's rather standard.
Okay, that makes sense. Thanks.
So just following on from that,
Yes.
the one thing that just seems a little odd, like you said, that the key quantity in a single round is the von Neumann entropy, and not that the key quantity in a single round is the von Neumann entropy and not like a smooth min entropy, where the latter typically is what you expect in like a finite size kind of setting. Like, is it obvious why the von Neumann entropy rather than the smooth min entropy is kind of the key quantity?
Okay, yes. So I think there is a confusion here. So the smooth mean entropy is the relevant quantity in total in order to know how much we can extract. Okay? But I don't know of any technique that somehow shows that what you need, that in order to get a total smooth mean entropy, what you need to count is the smooth mean entropies of just one round each time. Okay? And I mean, if there is such a technique, then it's fine to do it with the smooth mean entropy. I wouldn't say it's easier or more complicated one way or another. But there isn't. Okay, so either you somehow do, I mean, the previous works, either they really try to prove security and analyze what's going on round after round, or in the proof by Carl here, there is a different quantity that has to be bound, and this is some other type of entropy. But I don't know of any proof technique or any chain rule that allows us to really think about the smooth mean entropy in just one game and relate it to the total entropy.
All right, let's have one last question while Anne is setting up her computer.
So it looks like using this new chain rule, you are somehow not using the existing infinity theorem to go from IID to the most general case. Can you use the same for other QKD protocols?
So is the question if I can use the same chain rule for other QKD protocols?
Yeah, same technique for other QKD protocols.
You mean not device independent or
Yeah.
in general?
Not in general.
So yes. So you can use it for for standard QKD. You can use it for other device independent protocols. Yes, I mean there is a specific way of using this chain rule, and we explained in the paper. But yes, it's a very general chain rule. It's very useful. It's a new. So this is the entropy accumulation. You should look it up.
All right, thank you very much again, Rotem.